Hi, I'm Braylon Nix, and in this video, I'll be presenting my implementation of two quantum protocols on a Google Colab file using Qiskit. Uh, the overall goal of the assignment is to demonstrate how quantum circuits can encode, transmit, and recover both classical and quantum information using entanglement. But more specifically, the goal is to extend the 4-bit superdense coding and 2-qubit teleportation examples that we covered in class to 6-bit superdense coding and 3-qubit teleportation. At the top here, I have a setup cell, which is to be run first, which just installs the required packages of Qiskit and imports uh, different tools such as Air and Matplotlib and NumPy in order to do the drawings and some of the calculations. First, we'll look at part A, which is the 6-bit superdense coding section. Um, Superdense coding in general is a protocol where we send two classical bits using just 1 qubit. And in the example, provided that Alice and Bob share an entangled pair of qubits in advance, this can be done. In the assignment, we extended it to 6 bits using 3 Bell state pairs. And if you look at the code here, this is just actually repetitive. It imports some of these packages again. But here's a function where we create the 4 different 2-bit states represented as qubits. And then here is a larger function that builds the actual quantum circuit, all of the gates to perform the operations for the superdense coding. And then we convert the message at the bottom. And then here's just where you can actually implement a specific message. You can change it to any 6-qubit message. And it works better in these Google Colab files to put the drawing of the circuit into a separate code cell. So that is done down here. This is the cell drawn from uh, this whole section of code here. And if you look and compare it to the example for 4-bit superdense coding that was shown in class, it's very similar. Each pair of qubits, for instance, Q0 and Q1, Q2 and Q3, and Q4 and Q5, are entangled at the beginning using a Hadamard and C0 gate. And then Alice applies operations on her 2-bit message chunks based on what the qubits are supposed to be, and then Bob performs the measurements on each of the qubits to decode the message. Um, Down here separately is plotting the histogram for the results. And if you see for the simulation, which we just set, you set the count number right up here where it says shots equal 1024. All of the 1024 counts of running the simulation end up with 101011, which was the original message. So there's a 100% accuracy of this when run as a simulation. Now, obviously, this uh, this would not work in a real quantum circuit due to decoherence from the environment or within the circuit itself. And then here, this last cell just prints the actual counts, which there are 1024 counts of the actual message that was sent. And then you have the most likely outcome, which is the same as the original message. the recovered message here, it's just in reverse order, but the outcome, it flips it back to the correct order that it was sent in. Okay, now let's move to the second part, which is three-qubit teleportation. Teleportation allows us to transfer an arbitrary quantum state from Alice to Bob using shared entanglement and classical communication. And this protocol is the one that's fundamental for quantum communication and quantum networks. And if you look, there's a little bit of redundancy here where we import some of the same things over again. But there are some things that need to be imported for this, such as state vector that we didn't use in the prior section of code. This first function just prepares the three-qubit message, and then the teleportation code, which is the bulk of it, and saving the final state vector, um, as well as calculating the fidelity, is all this larger function here. And if we scroll down, this is the drawing of the teleportation circuit, and it looks a lot more complex, but again, it is essentially just an extension of the two-qubit teleportation example that we did in class. Qubits 0, 1, and 2 store the quantum state that we want to teleport, and then qubits 3 through 8 uh, create the Bell state pairs between Alice and Bob. Alice performs the Bell state measurements on her qubits and then sends the classical results to Bob. And then, based on these results, Bob applies these correction gate X and Z operations here at the end that are highlighted to recover the original states. And after this is just the state vector at the end here. It just wouldn't fit on this first line. But after running the simulation in Qiskit, we compute the fidelity of the teleportation, which is similar to the counts and the histogram up above. Um, a teleportation fidelity of 1 means 100%, which is near perfect teleportation. If you look here, it says the calculated fidelity for it is 1.0, repeating 4 here at the end, probably just a rounding error. But this shows that the protocol successfully transfers the three-qubit state using entanglement and classical communication. However, like the above example, in a real-world scenario, you have to deal with uh, decoherence from quantum noise in the circuit or from the environment that would decrease this fidelity. In summary, we implemented and simulated both of these fundamental quantum protocols in Qiskit. The 6-bit superdense coding successfully transmitted 6 classical bits using 3 entangled pairs, and the 3-qubit teleportation protocol transferred a 3-qubit quantum state with high fidelity. And this ultimately demonstrates the power of entanglement in quantum communication. Thanks for watching.